Uh, we, we have we have for our pleasure this afternoon two of our very own HASP member Richard Swanson and John Coves, also a HASP member, will be doing a tag team for us. Richard spent 35 years as a medical educator and clinician in the fields of internal medicine and rheumatology. He holds an MD from Creighton University and did his residency at the National Medical Center. Richard spent many years on the faculty of Indiana University, the University of Illinois, Michigan State University, and the Western Michigan School of Medicine. John Coves, our other presenter, is a board-certified periodontist. He received his DDS from the University of Iowa and his specialty education from the University of North Carolina. He was in private practice in Holland from 1977 to 2017. And during his career, he served as president of Midwest Society of Periodontology, covering 11 states, and is also president of the American Academy of Periodontology Foundation. So without further ado, here we go. I think Richard's up first.
There, can you hear me now?
Yes.
Okay.
John,
Well,
do you want to begin sharing screen again, John?
I'm
Yes.
working on it.
Okay.
My assistant has left me here.
Well, now she just left your wife, so
There we
she's
go.
coming. There you
there
go.
we go.
Oh, got it. We're on board.
Okay.
But you've heard our introductions, or otherwise known as Statler and Waldorf. And everybody, welcome back to the Muppet Theater of Science. Let's move along here. You know who we are. Let's move into slide number 3. We're going to lead off with the miasma theory. So this talk is about the war against microbes or the war against germs. And this war began a long, long time ago. Originally, the theory of infectious disease was called the miasma theory. And the miasma theory is based on the concept that poisonous vapors were rising from stagnant waters, such as swamps or open sewers and things like that. And that was, these poisonous vapors were what caused infectious disease among people. And this theory dates back to the Middle Ages, if not beyond, into ancient Rome, very possibly. And as an example of that, during the Middle Ages, there was a belief that the Black Plague, bubonic plague, had been caused by vapors filtering down to the surface of the earth from a comet, which would be completely in line with the miasma theory of infectious disease. The germ theory came along much later. It had its beginnings in the 1860s, but it was first suggested by Dr. Louis Pasteur. He couldn't prove it, it was proven later. But the concept of germ theory, which everybody should be familiar with, is that germs are found in the environment and they enter the body through an open wound and will cause disease, particularly gangrene. That is the genesis of the germ theory. What's a microbe? Well, a microbe is a microorganism. It's very, very small. You can't see it without a microscope. They weren't discovered until the microscope was invented. Germ can be a single cell or a colony of cells, and it includes bacteria, protozoa, fungi, algae, and viruses. Microbes are not the same as germs. Germs we're going to use as a term to imply a microbe that causes infection or illness. A microbe, like a single cell organism generally, think of it as a Lego block. And in comparison, the human body itself is made up of 137 trillion Lego blocks. Now, those are just native cells to the human body. That doesn't include passengers on the human body, which would be part of the human biome, the bacteria that are in your intestinal tract, that are on your skin. There are trillions and trillions of those bacteria with us also.
Now, let's talk about the giants of the germ theory, give you a little background. Anton Van Leeuwenhoek was a Dutchman. He developed the first microscope, and we'll see microbes at the first time. Ignaz Semmelweis was a Austrian who was a obstetrician, and he learned about washing hands between patients to prevent spread of puerperal fever. Joseph Lister began by sterilizing his instruments. Joseph Pasteur was, as we said, the first one to describe germ theory. And John Koch, it's H-O-C-H, or K-O-C-H, John Koch was another giant. Next slide.
Before we move on, I apologize for the typo. It's actually Louis Pasteur. I forgot to repair that.
Louis Pasteur and John Koch. We got some misspellings here. We didn't catch.
K-O-C-H.
This is Anton Van Leeuwenhoek. He was a Dutchman. He was a self-taught oculist. He learned how to grind lenses, and he developed the first microscope. It was allowed us to see microbes. He didn't know what they were, but he did describe them, and we knew that they were there. Next slide. He was the, as I said, the first microscope. This was in the 1600s in Holland. They were well known for their grinding lenses and for their early science. The next one is Ignaz Semmelweis. He was a obstetrician, and he was noting in the wards that many women, after they delivered, were dying of puerperal fever or birth fever after they delivered a healthy child. And next slide. He found out that if he washed his hands between patients, that the incidence of Semmelweis would drop considerably. It turned out that the germs that these women were contracting was carried by the hands of the physician. They would be known to come in to the delivery room, deliver the child, go up to the morgue, do some dissecting, and then come back down to see the next patient without ever washing their hands or changing their clothes. He found that if he washed his hands between patients, the patients were not infected. Next slide. This is Joseph Lister. Joseph Lister was a surgeon. And next slide. He found that if he sterilized his instruments before he went to an operation, that there would be much less disease spread. This is a picture of a drawing of him in the operating room. This is the first patient in which he did. It was a young boy who'd been hit by a car, and he was going to lose his leg, and it was amputated, but with sterilized instruments, so that the boy survived and didn't develop postoperative gangrene. Next slide. As he stated here, surgeons arrived in the operating suite in their street clothes without even washing their hands. Anesthesia had allowed them to do more, but infection was still a constant threat. The miasma theory still persisted, but in 1865 at the University of Glasgow in Scotland, he read the works of the French chemist Louis Pasteur, who postulated that germs could explain the infection. Lister began to look for a chemical to sterilize his instruments. He came across carbolic acid, we now call it phenol, and he found that they would kill the germs. He then laid out a protocol to sterilize the instruments, the hands of the surgeon and the nurses, the dressings, and the actual wound with phenol. He used this technique to heal the open fracture of this child hit by a car without an infection. Next slide. It was not quickly accepted. Lister was poo-pooed. Example we have here is our good friend, Dr. Bliss. Dr. Bliss is from Grand Rapids. He was a Civil War surgeon who stayed around in Washington and became known as a trauma surgeon. He was called in to when President Garfield was shot, and Garfield was felt to would have survived if Bliss hadn't continually probed the wound in his back with his dirty hands. Ignorance is bliss. That's where the term comes from. Goldsmith in the Civil War began using bromine, and he published this, but again, it was not accepted. He showed that he had a dramatic decrease in post-operative infections in amputations from this. Next slide. We're going to skip to Robert Koch. He's a German, as you can see. Robert Koch was a bacteriologist. Next slide. He was called the father of modern bacteriology. He discovered that bacteria cause diseases. He discovered Koch's postulates. We'll show that in a second. And he discovered the bacteria that cause tuberculosis, cholera, and anthrax. And he received the Nobel Prize for Medicine in 1905. He also demonstrated that dry heat and steam would sterilize the instruments as effective as the chemical antiseptic killing germs. He developed laboratory techniques, bacteriologic growth media, which we call agar, and he, along with Petrie, John Petrie, developed the Petri dish, which we use in the laboratory to grow. Gustav Neuber used Koch's techniques to establish an aseptic protocol in the operating room. And in the United States, Johns Hopkins in 1890 began using surgical gloves. The bare hands were not exposed. Dr. Halsted, who was one of the famous early breast surgeons, the Halsted technique, developed this and accepted it. Next slide.
You know, one of the things that we should mention is that Dr. Koch's postulates are actually what proved germ theory. That's what turned the corner for us scientifically.
Let's take a look at those Koch's postulates. Basically, what happened if germs were infecting a person, we should be able to culture the germs from the infected person in a pure culture. Number two, we should be able to then re-inoculate them into another experimental host, not a human, but mainly mice, and develop the same disease as the first person. And the fourth one is you should be able to remove the bacteria from this last person and show that it's identical to the first patient's disease germs that we found. Koch's postulates have been disproven somewhat lately, and we know that some of the viruses don't follow Koch's postulates, but this gave people a chance to know how to decide whether a specific bacteria was causing a specific disease. Next slide. Paul Ehrlich. Paul Ehrlich was a scientist in the early 20th century. He described that there should be a specific drug, not known what they were yet, that would kill a specific disease. He called this the magic bullet, and this was his claim to fame. He also received the Nobel Prize for much of his work. Next slide. John, you're on.
We have a whole arsenal of weapons that we use in our war against microbes and germs. Disinfectants, antiseptics, antibiotics, antivirals, and vaccines. And we're going to go through these a little bit later to describe them. We talked about Joseph Lister, and the product Listerine is named after him because it's an oral antiseptic. However, he had nothing to do with its invention. They stole his name, and to my knowledge, his descendants never got any royalties for that. The active ingredients for Listerine, for those who are curious, are essential oils, and alcohol. The essential oils are menthol, eucalyptol, and thymol. And alcohol, which is, we all know is a very good antiseptic, is 21.6% alcohol in Listerine. So there's some potency there.
That would be called about 48 proof.
Yeah, that's for sure. We're going to discuss the difference between asepsis and antiseptic, antiseptic and disinfectant. Asepsis really means the tissue is free of disease-causing microbes or germs. Essentially, think of it as aseptic technique in surgery means the instruments have been sterilized. And sterilization is usually dry heat or steam autoclave in current times. I think there's even a chemical version of an autoclave. Antisepsis is the prevention of disease on human tissue. And an example of that would be a surgeon would paint the skin of a surgical site with betadine prior to beginning the surgery. And that's not only going to kill bacteria that are on the skin right then, but there's going to be a substantivity or staying power of that betadine to keep the area free of germs as the surgery progresses, and then afterwards as the healing begins. An antiseptic and a disinfectant do roughly the same things. The primary difference is potency. An antiseptic is something you use on living tissue, and examples of that be iodine, hydrogen peroxide, alcohol, soap, mouthwash, betadine, chlorhexidine. Those are all really good antiseptics. Disinfectants are designed to kill bacteria also, but they are much stronger. You don't use them on living tissue. You use them on doorknobs, surgical tables, things like that. And two really good examples of disinfectants would be Clorox and Lysol. Neither of which are supposed to be taken internally, by the way, just to be clear on that. On the left is a disinfectant. This would be a generic version of Tidy Bowl for your toilet. And on the right would be antiseptic. This Purell, which we all use now. We find every place we go. And just a little logo we threw in here on antiseptic sanitizer to be sprayed on surfaces, not on people. Well, not on people. Well, antiseptic on people, but disinfectant on surfaces. An antibiotic and an antiseptic are two different things. An antiseptic prevents growth of bacteria on the skin and other surfaces. An antibiotic is designed to kill bacteria within the body. There's all different kinds of antibiotics, antifungals, and other medications, which we will get into as we progress. I think you're up.
Antimicrobials, which are antibiotics, antivirals, antiparasitic, and antifungals. These are all drugs, which are chemicals, which kill these specific microbes that we mentioned earlier. Next slide. Antibiotics are chemicals, as I said, to help stop infection caused by the bacteria, either by killing or keeping them from reproducing. Antibiotics disrupt essential substance or structures of the bacterial cell wall. So antibiotics are for bacteria, not viruses, not fungi, and they're specific for bacteria. We'll talk about that, how they've been misused by many of us physicians for years because of the general population's misinformation. Next slide. This is Alexander Fleming. Alexander Fleming was an American, or actually British, bacteriologist who was really studying streptococci. And you see these dishes that are piled up there. These are the Petri dishes that Koch and Petri developed. So what he did is he plated he had a Petri dish that was left open on his desk and near an open window. He went away and came back. Next slide, please. He left a Petri dish of this bacteria uncovered and sitting near an open window. The next morning, the Petri dish had become contaminated with mold through the air. Around the mold, however, the bacteria had died. This mold produced a juice, as he called it, which he called penicillin. This was the first antibiotic. Next slide. What he did is, this is a Petri dish on the right, which has been plated and streptococci are growing. He put a disc, it's a little cellulose disc on the left, a little white dot on top of it, and that disc contains penicillin. And so you can see the zone around here that of the bacteria that had died. So we know that this streptococci, or whatever else we plated on there, is now killed by the penicillin. Next slide. Here's how we tell. We send a specimen to the laboratory, and it's plated onto a growth media, which we see in blue, and then these antimicrobial discs. This may be the same antibiotic, but in different strengths, are placed on the agar plate and allowed to incubate, and then we measure. You can see that there is a small amount of white circle around one on the top left, and then they get particularly bigger, and we measure this. It tells us either the antibiotic that was on these is killing this germ, or the various strengths of the same antibiotic that is killing, and so we know which strength we should recommend to the clinician to use to treat the patient with. Next slide. We also look at bacteria under the microscope. We do it's called Graham's stain. Graham was a bacteriologist who developed this stain that was placed on a slide, and it caused the bacteria to either become blue, which is Gram positive, or red, which was Gram negative. This gave us an idea of what kind of antibiotics to use, because certain antibiotics killed only Gram positive organisms, and some antibiotics would kill both Gram positive and Gram negatives, or just Gram negatives. Next slide. Now, how do the antibiotics kill the bacteria? Well, most of the time, they interrupt the cell wall of the bacteria, allowing the bacteria to kind of spread out and die. They also go after the other things like folate synthesis in the cells or the DNA, but mainly they attack the cell wall. We look over on the left, we see beta-lactams. That's the kind of antibiotics that includes penicillin, cephalosporins, carbosporum, and monobacteriums. Vancomycin also works there. A number of other ones like tetracycline break up small portions of subunits in the cell of the bacteria. So it kills the bacteria by interrupting some of its mechanisms of living. Next slide. Now, we find that in antibiotics, we are two kinds of antibiotics, bactericidal and bacteriostatic. Bacteriostatic means that they just keep the bacteria from reproducing. So they may still be there, but they're not able to reproduce. And then the bactericidal, they kill them. Now, based upon their spectrum, which we talked about before, what kind of bacteria they kill, we either have broad spectrum, which means they cover a lot of bacteria or microbes or germs, and there are narrow spectrums, which means that they're only good for a specific organism. Next slide. Now, this is just a show of how these were first developed. These are mainly cephalosporins, which are another beta-lactam, different than penicillin, We had many penicillins, but it shows you we had the first generation of cephalosporins. Then the second generation came along, third and fourth. And we actually have now combinations of these and other antibiotics to kill germs that are particularly difficult. What we have is found that many bacteria were exposed to antibiotics, and it didn't kill them, but they caused the bacteria to mutate and become resistant. That is, we'll talk more about, because that's a major problem today. We have certain bacteria. I'll give you an example. Let's talk about pneumococcus or pneumonia. It used to be killed very easily by penicillin alone. Today, it's been exposed to penicillin so many times that it has mutated, and now we have to take 2 and 3 drugs to do the job that one we did in the past. Next slide. John?
All right. Let's talk about the trends of emerging infectious disease over the past century or so. Since 1900, there's been a huge shift in disease mortality from infections. In 1900, 800 out of every 100,000 infected people were going to perish from that infection. By 1960, that number had been reduced to 50 out of every 100,000. In low and middle income countries, third world countries, childhood immunizations have decreased mortality by 80%. There's been a 50% decrease in childhood deaths, a 60% decrease in deaths from malaria, 40% decrease in deaths from HIV, and wild polio has been almost eradicated. Smallpox has been eradicated. Now, how did we do this? Well, we did it through immunization, through antibiotics, through antifungals, vaccines, antimalarials, disinfectants, and antiseptics. All of these have been the weapons that we've used to, in the past 1.25 centuries, to achieve these kinds of results. This is where science has taken us. HIV, there's no vaccine for that. There are antivirals to treat it. There's antimalarials and all kinds of antibiotics. So let's move on. Viruses, there are thousands of viruses. You couldn't see them until the invention of the microscope. And the microscope wasn't invented until 1932.
This is the electron microscope.
Electron microscope. Thank you, Richard. The electron microscope, which doesn't use refracted light, it uses a beam of electrons for magnification. Viruses are different from bacteria in that viruses have no cell wall. It's just a bag of protein surface. A virus has no organelles like a cell does or a bacteria does. There's no nucleus, no Golgi apparatus, no endoplasmic reticulum. That's hard to say sometimes. None of the normal organelles that you would find inside of a cell exist inside of a virus. We thought we'd throw this up there. This is what some of the viruses look like. My favorite one is the one in the middle. I think that's Richard's favorite too. That's a bacteriophage. That's the type of virus that will attach itself to a bacterium. The bacteria is the actual host here. I like this one because it looks kind of like the moon lander. But you can see the different shapes and forms of these various viruses, the adenovirus, the Ebola virus, influenza, hepatitis, and so forth. We don't even have the coronavirus on here, but we will show pictures of that later on. How do viruses replicate? Well, a virus is incapable of replicating on its own. It has to have a host, and it attaches to the host and injects into the host its DNA or RNA. The host cell becomes a factory that reproduces copies of the original virus until eventually the cell dies, it breaks open and spills out all the new viruses. They call it apoptosis. It's when a cell dies and bursts open. That is how a virus will replicate itself. It can't do it without a host cell. This is just an overview of many of the infections that can occur with viruses. And you can, these are quite a lengthy list of them here. There's measles, mumps, herpes, hepatitis A, B, and C, smallpox, chickenpox, influenza, polio, rhinoviruses, which cause the common cold, and of course, coronavirus, which is a SARS virus. It's responsible for COVID-19 infections. Antiviral medications are available to treat viruses, but there are not very many of them. They're fairly rare. There's only about 100 available in this country. These drugs will, the problem with antivirals is a drug that can kill a virus can kill a host cell as well. So there's a toxicity here. As you know, viruses cannot be self-propagating, and they're really hard to grow too. Any drug must block a virus's ability to replicate especially before mutation occurs. If a virus sticks around long enough, it will mutate. We're seeing that with coronavirus right now, the COVID-19. We do the Brazil version, the United Kingdom version. We're dealing with the Delta version right now, and there are others. So there's a gamma version coming around now. If a person is already ill with a virus, generally speaking, an antiviral is too late to impact. Of course, it's not going to help very much. So ultimately, in dealing with any viral disease, any viral infection, vaccines is going to be the answer now and into the future for any foreseeable time.
Making a virus.
By the way, this is a coronavirus.
This is a coronavirus. We realize that the coronavirus, if you look at it, has these spikes on the left side sticking out from the membrane, and there's the DNA in the middle. So we can use the whole virus to make a vaccine. We'll talk about how it's done, or we can use parts from the spike proteins outside, or we can just get a hold of the genetic material, whether it's DNA and RNA, to make our vaccine against this. Now, today we have many vaccines. Smallpox, next slide. Smallpox, measles and mumps, COVID-19, which we are now trying to get everybody to immunize, hepatitis A, B, and C. Getting ourselves immunized against hepatitis is very important. Influenza virus, get your flu shot. Tetanus toxoid. HPV, which we're trying to get young people, because we know that HPV virus in some people can lead to cancer. Yellow fever, meningitis, meningococcals, rubella, dengue fever. Dengue fever is not something we see here in the United States, but around the world, it's a very, very major health problem. And we know that the veterinarians are way ahead of us. They have multiple animal viruses. There's feline leukemia virus. There's viruses for mother pigs and for baby pigs. So they have developed vaccines for many, that's why of these illnesses that affect animals. And their research and how they worked on it is really miles ahead of what we've done in humans. Next slide. Now, how do they work? Well, what they do is that we make antibodies. So these antibodies, which are in kind of a violet color, attack the antigen and kill them, so that the vaccine is made to go against these products, whether it's the spike proteins or the DNA or RNA, which we'll talk about. And we develop antibodies. Our body recognizes these as foreign. The B cells kick in and they start to make antibodies, so that when you are exposed to this virus, again, boom, it recognizes it and marches in and kills it off. Next slide. Now, let's take a little history of smallpox. Smallpox was first described, smallpox, small meaning, and there's many other diseases that have poxes with it. Syphilis has them, many other cowpox, but before 30 BC, it was recognized that smallpox was a specific disease. And it marches on. Next slide. What we found was that in 1777, George Washington wanted his troops inoculated against smallpox. Smallpox was a scourge of the military. We had learned how to, we called it virilization. We took a knife or a sharp instrument and made a small cut in the receiver. We took a little bit of the pus from the vaccine and from the pox and smeared it into this new patient, and he made antibodies against this. It was first discovered in London, and it was noted that milkmaids were not getting smallpox because they were exposed to something called cowpox, and it was very similar to smallpox. So they realized that sometimes using cowpox pustules would work just as well. Next slide. Well, down here, okay, we'll back up. We find out that there was a great deal of anti-vaxxers. You can see down the lower right side, 1801 to 1803. This was do not get vaccinated. This was a war. So you see the anti-vaxxers have been around now probably for over 200 years. Next slide. In 1952 and 53, we found that they developed, Louis Pasteur in 1879 discovered what these bacteria were. And then in 1954, you can see there's Jonas Salk holding up his polio vaccine, followed by Sabin's, which was an oral vaccine against smallpox and polio. Poliomyelitis was a similar disease. Next slide, please. You can see that there was still, in 1958, we were still battling with the public's view of these diseases. Be vaccinated this New Year's against smallpox. Then we came along and we started to vaccinate against polio. Next slide, please. So then we're kicking polio out. I can tell you that there's only 2 countries in the world in which wild polio still exists: Pakistan and Nigeria. There is polio and elsewhere, but it's a different kind. But wild polio has been very worked on by the Bill Gates Foundation and by Rotary International. Rotary International has sent people out to these various countries, and they spend a month or so going from home to home vaccinating. In some of these countries, especially the Muslim countries, where a woman cannot be with another man, the wives have been very, very important. Now, in 2020, we came up with the COVID vaccine, which has been used against this SARS virus, which is COVID-19. Next slide, please.
Types of vaccines.
There's types of vaccines.
There's quite a number of them. Live attenuated vaccine, which means that the virus has been disabled before being placed in the vaccine. An inactive vaccine, which means the virus is dead. A subunit, a recombinant, or conjugate, or polysaccharide, which means a part of the virus is used in the vaccine. Toxoid vaccines, well, that would be tetanus. mRNA is what we're using now. This is state of the art at the moment. And that is the Pfizer vaccine and the Moderna vaccine. I think Johnson & Johnson is also an mRNA vaccine too. And the last one is a viral vector vaccine, which is, that's interesting. They take a harmless virus, attach to it a part of the infective virus. They use the harmless virus as the vehicle in the vaccine, which is, it carries the part of the infectious vaccine into the body where it is exposed to the immune system. The immune system recognizes it, the B cells kick in and start producing antibodies. So it's a viral vector. We use one virus to help protect against another virus, piggyback together. These are some various examples of the vaccine. The influenza vaccine, that's an inactivated virus. Pneumococcal, also inactivated. Tetanus is a toxoid. Diphtheria is inactivated. Pertussis is inactivated. Hepatitis B is inactivated. And so is human papillovirus. Measles, mumps, and rubella, that's a live vaccine that's been attenuated. And so is zoster. And we already know that the mRNA vaccines are Pfizer and Moderna.
Now, the COVID-19 vaccines, we wanted to show you this because they've used all of the various techniques, the live attenuated, the inactive virus, the subunits, and the DNA and RNA, which is the mRNA virus today. We have taken the messenger RNA out of the virus and used the human body to make antibodies against this. This technique is not new. This is one of the things people are opposed to these new vaccines, saying the techniques are so new, but in fact they are been around since the 1990s. We've just now started to use them, and so the techniques are not new at all. Next slide. Now let's talk about the non-vaxxers versus the anti-vaxxers. Next slide. Non-vaxxers are those who haven't got their vaccine. This is the 1930s. This is the anti-vaxxers jumping off the cliff because of misinformation. And this shows you that we've been doing this, having these opposition to vaccines for many years. Just recently, in a parade here, I think in New Zealand, there were a group of people carrying signs against vaccination, saying that they used fetal tissue. And so it was human fetal tissue. This is not correct. There is no human fetal tissue involved whatsoever. Next slide. Most non-vaxxers are the most common causes concern about the safety. But they're worried about this, quote, new technique. Well, the mRNA technique was developed 20 years ago, and safety has been proven many years ago. So much of the non-vaxxers' concern is really not appropriate at this time. Next slide. Anti-vaxxers. Now, these are a little bit harder people to deal with. Religious beliefs that God will treat you. The risks of this vaccine outweigh the benefits, which we've proven not to be the case, and we'll show you some data here. They also believe that pharmaceutical firms can't be trusted. They also question about autism. This has been disproven. This was back from a Lancet article many years ago that we thought that the vaccines were causing autism. In fact, we know they aren't. The other thing is they say vaccines aren't necessary anymore. We can fight this off. Well, look at how many people have died. And I guess the vaccine, we really do need to prevent those deaths. They also mistrust science, period. They just don't believe what Dr. Fauci and other people like ourselves are saying. John?
Well, this is where I'm supposed to share a story with everybody. This is a parable, if you will. And it was actually told to me many years ago by a pastor. I can't even remember who it was now. And the pastor told this story to me. And imagine a town where on a river, there's a terrific flood. And water's rising and rising, and this man climbs up on his roof to escape the flood. And eventually a boat comes along, a rescue boat, to save him. And the man said, "Well, I'm not getting in the boat. I don't trust it. And I've been praying and praying to God, and God will save me, so leave me alone." So in frustration, the boat motored away to save other people. A little while later, the water got higher and higher. A second boat came to that man on the roof and tried to rescue him. And once again, he said, "No, I've been praying to God, and God will save me. I don't need you." That boat left also. A little bit later, now the water is almost to his feet. It's up on the peak of the roof. And a third boat comes by. And again, the same discussion occurs. And once again, the man on the roof said, "No, I've been praying, God will save me." The boat left. Not too long after that, the flood rose even higher, swept him off the roof, and he drowned. Flash forward, he's in heaven, standing before God. And he says to God, "God, I don't understand. I prayed and I prayed and I prayed that you would save me, and you didn't." And God looked at him and said, "My son, I sent 3 boats. So think of the vaccines as our 3 boats." You're on, Richard.
Next slide, please. This is one of the risks that people claim of blood clots. And if you look at the AstraZeneca vaccine and you see the percentage of people per 100, there was 4 cases per 1 million. If you look at birth control pills, and it caused a much higher rate of blood clots in the lungs and elsewhere. Cigarette smoking contributed a much higher rate. And then if you look over the far right, what the COVID vaccine itself did, 165,000 cases in 1 million people. So you can see that the risk of a blood clot, which we have seen, is very, very, very low from the vaccine. Next slide.
I'm back up again. Some of the resistance to vaccines have been due to conspiracy theories. You heard one already, which was that fetal tissue is used. Another one, which I have seen and heard on the radio, and this is QAnon type of stuff, is that it's a plot by the government and by Bill Gates himself to use the vaccine as a vehicle for a microchip to be placed in the body so that people can be tracked. And this is a very big concern for people who have bought into this conspiracy theory. Well, I'm showing you a slide here. This is a typical syringe. This is actually not the kind of syringe they use for vaccines. Vaccine syringe is a 30 gauge needle, which is much smaller than this needle. And you can tell from the photograph, this is a fairly small needle in itself. It's much larger than a vaccine needle. A microchip is about the size of, or maybe a little larger than a grain of rice. And no grain of rice is going to pass the bore of this needle. It's just physics dictates that is simply not possible. The microchips that are implanted in pets, for example, aren't transmitting microchips. They just contain information. And they tell the name of the animal, the name of the owner, phone number of the owner, address of the owner, and the vaccine history of the animal. For example, if the dog has been vaccinated for rabies. That's what's in the chip. The chip does not have a power source. It doesn't transmit, doesn't have Bluetooth capability or Wi-Fi capability. It has to be scanned in a veterinary office to find out the information in the chip. This is a chip that was placed in somebody's hand, similar to placed into a dog. And if you look carefully, right here, that is where the chip was placed. It looks like it was placed in there with a bore of a needle about the size of a drinking straw or a paper punch. And it's quite a bulge in the tissue there. I humbly submit that the use of a vaccine to administer that kind of a chip or any other kind into the body is quite impossible to do. Now let's put that conspiracy theory to rest. Yep.
Now, University of Texas recently did a study on 1,300 persons to appraise their knowledge regarding the causes of autism compared to science. That actually wasn't autism as well, but their knowledge level of vaccines. Next slide. Next slide. There, oh, here we go. 71% of those who were in the study accepted misinformation. They felt, who accepted misinformation, they felt that they knew more than their doctor. This misinformation was better than what their doctor could tell them. Their inability to accurately appraise their own knowledge level, which is this is called the Dunning-Kruger effect. They were not able to realize that their knowledge was misinformation. Most accepted celebrities' information over the doctors. And Madonna could tell them more than Dr. Fauci. They had lack of knowledge of their own misinformation, and they allowed their beliefs to adversely affect others. Measles, diphtheria. We've seen this now in the spread of the measles virus and in New York City, in some of the certain ethnic groups. They were all anti-vaxxers. They did not believe that vaccines were healthy or good or should be done. Next slide, John.
Well,
actually, back slide.
We go back, before we go back, this is where I'm supposed to tell my other parable, my story.
Please.
As you all know from our introductions, I was educated in dental school at the University of Iowa. And I had some friends over at the medical school. And one of those friends graduated, became a family practice physician and set up in a small town in Iowa. I took over the practice of an established doc who had had enough. He retired and moved to Florida. So here's this friend of mine. He's a young doc. And he's telling me this story. He's in his office, and in comes one of his patients he inherited, a well-established farmer, very successful farmer in the community. And Iowa farms are very large and very successful, generally speaking. And this guy came into the office and with a runny nose and sniffles, and said to my medical friend, "Hey doc, I'm not feeling well. I want you to give me an antibiotic so I feel better." And this young physician said, "Well, I'm not going to give you an antibiotic. If you have a cold, which is viral, an antibiotic will not impact a virus of any kind, particularly a cold." And the farmer became a little bit irritated and was insistent. He wouldn't let up. I know my body. I know what I need. I need an antibiotic, and I want you to write me a script. So finally, in frustration, my friend said to this farmer, said, "Okay, which antibiotic do you want? Do you want penicillin, tetracycline, erythromycin, Z-Pak, cephalosporin? What dose do you want? 100 milligram, 200 milligram, 250s, 500s? How many of them do you want? 10, 15, 30, 100? How often do you want to take them? Once a day, twice a day, 3 times a day, 4 times a day? What's your pleasure?" And as related to me by my friend, he said, the farmer looked at him and said, "Well, you're the doctor, you decide." And my friend came right back at him and said, "You're exactly right. I am the doctor. I'm not giving you an antibiotic. Will do you no no good at all. Go home, get some rest, push fluids, and I guarantee you'll be cured in 7 days. Bye. End of story. The problem with this, and this is a problem faced by physicians and dentists, is that patients oftentimes are insistent on a treatment that will not work. They're insistent. And too often, historically, we've just given up and pulled out the prescription pad, which we shouldn't do, shouldn't ever do. That's my little story. Let's go back to that slide we jumped over.
Well, the reason that's a good example that John told of why we've developed resistance to antibiotics. We give somebody an antibiotic, for which they don't need, but the body and the germs that are in the body and around the body see these antibiotics and they develop resistance to them. So today we've had to use much more powerful antibiotics, much more broad spectrum, with more potential side effects and more expensive. Now, the anti-vaxxers, I just want you to see, these are 3 of the main anti-vaxxer groups in the United States. So if you see any information coming across with Informed Consent Action Network, that's an anti-vaxxer. The Children's Defense Fund, which is against immunization of children. This was founded by Robert F. Kennedy Jr. He surely didn't get his father's brains. And the National Vaccine Information Center. These are all 3 that are sending out literature. You'll see them on the press in various speakers, and should be aware that these are all anti-vaxxers. Next slide, please. Our final thoughts: man and the environment are in a constant battle for survival. We found that out. Man has found ways to control germs, but not all of our efforts have been beneficial or successful. And some of this is why some of our Americans, particularly those of color or Hispanic background, are hesitant to accept this. One, doctors have mistreated them, taken them lightly. We see the Tuskegee experiment, in which these farmers in Tuskegee, Mississippi, were given syphilis. Were given it. Half of them were treated and half were not. And they followed those who are not through their lifetime and see how they suffered with various complications. And they really don't trust white doctors. John, next slide.
Well, we mentioned the promiscuous use of antibiotics a few minutes ago, and many of you have seen in the news that the World Health Organization, WHO, has really raised the alarm about this. And as Richard had said, the overuse of antibiotics, when not appropriate, has resulted in what we call superbugs, which are very hard to kill and now sometimes lethal. And 2 examples of that would be MRSA, which is methylpenicillin-resistant Staph aureus. Staph aureus is a very common bacteria. And on my arm right now, there's probably some Staph aureus. Same with all of you. It's not a rare bacteria. However, the MRSA strain of it is a problem because if it gets into a wound and causes an infection, it is very, very difficult to treat. People in the hospital with MRSA infection are put into isolation, and the nurses and physicians who attend that person have to gown up just to walk into the room. Another example of a resistant bacteria, a superbug, would be Clostridium difficile, C. diff for short. C. diff can occur in the intestinal tract. That bacteria is in the intestines in everybody anyway, but it lives in harmony with all the other bacteria in the biome. And in some people, if they have a heavy dose of antibiotics, well, one of the things antibiotics does is, well, it's very effective in killing targeted bacteria. It's also going to have an effect on other bacteria that are not harmful. It's going to alter the biome. And in some cases, that alteration of the biome biome is so intense that it creates a space, there's a gap, a donut hole. The bacteria in the intestinal tract live in harmony with each other. They compete with each other for space. And if you disrupt that competition, if you take a certain number of competitors out of the equation, an opportunist can blossom in the absence of competition. And that's exactly what a C. diff is. C. diff will flourish in the absence of competition from other bacteria that would normally be there, that are no longer there. And C. diff is also very, very difficult to treat. It can be treated, but it's difficult. In some cases, in extreme cases, they have actually used fecal transplants from a healthy person to someone with C. diff to try to reestablish a normal biome, because the antibiotics alone were not taking out C. diff. So the moral to the story is the continual war against bacteria is tricky. It requires the judicious use of medications, antibiotics in particular, but others also. And it should be done with safety in mind and be evidence-based or science-based, not on, oh, I think I'll try this. I'm gonna throw spaghetti at the wall. That has led us into some very difficult situations. So with that, Richard?
Well, we hope you've enjoyed this journey through germ world and have learned something about it, learned something useful that will help you in your life. We're open, I think, to questions. So Bruce, you can field the questions, or Kim, whichever you want to, and we'll try to handle the questions as they come.
Right. I don't have any in the chat, so anybody can just, there's about 30 of us on, so it's a manageable group. Feel free to just unmute yourself and ask your question or comment now.
Well, I have a question for either of you. Early in the presentation, you mentioned that it seemed like the veterinarians were maybe ahead in terms of the development of vaccines for animals. And I'm not sure exactly what that means, but I'm curious to know if either of you have any sense of why that's the case.
I think I can answer part of that, Kim, is that they are dealing with a disease which is very broad, and their degree of specificity for these diseases is much less than for humans. So their vaccines are I'm going to say this, maybe a little cruder, but they are very effective against these diseases. But they've been very, very busy doing this because the economy of these animals is very important. But I'm going to say this, they may be a little bit cruder in their development of the vaccine than we are for humans.
So just a follow-up question on that, do you have any sense of what kind of rules and regulations they're subject to in that world? I don't have a clue, but it occurs to me that, they might not be the same as they would be for humans.
I think you're correct. Their requirements, they have to go through federal regulations just like humans do,
Okay.
the FDA, but they may have less demanding specifications for proof of the vaccine's effectiveness.
Great.
The clinical trials are probably nowhere near as intense.
Okay, good. Thank you.
I suspect animals are also less likely to sue.
Less likely to sue is correct, but
Well, you just gave me a chill.
I did have a question. You mentioned earlier in the presentation that viruses do not necessarily obey Koch's postulates. And it seems if you took a virus from one bacterium to another and injected it, or let it inject itself and then harvested it and put it in yet another one, it would behave the same. So it seems, so what am I missing here? Because it seems like that would work.
the problem is if you let them inject themselves into a bacteria,
Mhm.
which are called bacteriophages, and they use the bacteria as their host to replicate, it's difficult to obtain the virus and grow them. And that's the problem afterwards. We can't always grow them to inject them into another host.
They don't culture very well.
They do not culture very well. And if they do, it's very long-term and very, very tenuous what they do. Remember, back when the flu shots were being done, we used eggs as a medium for the viruses to grow, but not all viruses would grow in eggs. That's the problem. Viruses are very persnickety, and sometimes we don't know ahead of time. To give you an example about how viruses and bacteria are important, Dannon Yogurt, which was a brand name, but from another company, was having a great deal of problem losing all of their cultures. Their cultures had been taken over by viruses. So they had to learn how to kill the viruses. So that's why yogurt continues to be made today, because of this research done in the 1990s.
I have a question back on the animals. I read in the paper they're making a vaccine for the COVID for animals. Is this a problem? Are animals getting it?
Not that I'm aware of.
There have been some. I think that they're talking about large felines in zoos are vulnerable to COVID. And I don't know how serious the disease is in a large animal. Yeah, I just recently read an article in Scientific American. I don't know if any of you take that magazine, about the next generation of vaccines, which was for a COVID virus. If you can imagine, I don't have a picture in front of me right now of the COVID virus. It's got those stalks on it that look like broccoli. And this new generation that they're testing in mice now, they take the protein on the tip of that stalk. The stalk is what attaches to a host cell. And from there, the RNA is injected into the host cell. So that protein is the attachment protein on the tip of the stalk. And they can grow this protein, synthesize it, so it's recombinant, and put that into a vaccine, and it combined with a nanoparticle. So the nanoparticle is covered with this protein, and use that as a vaccine. And in laboratory animals, in particular mice, the immune response to that vaccine in mice was very robust, much more robust than Pfizer or Moderna. Now, it's not ready for humans yet. It's just being tested in mice. But I think that might be the direction that vaccinology is going to go, if this technology proves to be viable in humans.
I can add that there's another talk that I'm going to give later on called CRISPR. And CRISPR is a technique of editing the DNA or RNA in various cells, including plants and animals. And this is a technique that's being used to not so much to treat COVID, but to help detect COVID much more effectively and cheaper than we have it now. So hang on, and you'll hear more about that later on, I think next week. How's that for a plug?
There you go.
So I have a question about future generations of antibiotics. So are pharmaceutical companies interested in pursuing development of antibiotics, or will there be some other type of chemical medication antibiotics for bacteria?
Right now, the pharmaceutical firms are not jumping at the gun to develop new antibiotics for two reasons. One, the amount of work to develop these new antibiotics is extremely expensive and time consuming. Number two, the number of people who would need these new super antibiotics is very small. So there isn't really a market for it. So it's economic driven. But right now, I think the pharmaceutical firms are somewhat stymied because they haven't got the information to figure out how to do this and the economic desire to do it. Does that answer your question?
Perhaps we need a crisis to drive that, because as we all know, the NRA vaccine technology was first developed 20 years ago, but they had no application for it until 2020. And there it was. Everything went into hyperdrive.
That's why the vaccines were developed so rapidly, because the technique didn't have to be invented. It was there and they just used it. So that's really why these vaccines were able to be developed so quickly. And what people don't understand is the techniques are old, they're not new. And so this is not an unproven technique. The technique has been well proven, but people don't understand that.
No, and up until recently, there was no need to develop a mRNA-based vaccine.
No.
2020, and then suddenly the need was massive.
To look at this, an example, HIV, they've been working on a vaccine for HIV now for almost 20 years too. They still have not been able to develop a vaccine for HIV. It has just eluded them because of the technical difficulties and because the HIV is not a simple virus like the coronavirus is.
I have a question for you, Richard. I had to take a phone call, and so I missed sort of the rest of your, when you were talking about non-vaxxers and that there was a parade somewhere in the area recently where people were protesting vaccines because of their belief that testing is done on embryos or fetuses.
No, not testing, that the vaccines contain human fetal tissue.
Oh, okay. Is
It
there any
no
truth
evidence
to that for any vaccines?
None. Human fetal tissue has never been used to develop these vaccines.
So
But
where
this
do you
is
think that misinformation comes from?
the anti-vaxxer groups,
Okay.
the
QAnon.
QAnon groups. Where do these misinformations come from? I have no idea. They come out of somebody's head.
Amazing. Okay.
You know, there's no human fetal tissue involved. I mean, there's no aborted fetuses. There's no human involvement. This was all done, shall we say, biochemically, not using human tissue of any sort.
Would that same be true for not just vaccines, but antibiotics?
Antibiotics are chemicals,
Okay.
and they may be tested in certain tissue cultures, but they're not specific to a specific tissue.
Okay. Thank you.
Give you an example, though. I'll give you an example of what we have. They're called HeLa, H-E-L-A cells, which are a growth of tumor tissue that was removed from this woman, Helen. She had no idea, and these are perpetuated. These are cells used in the laboratory to test various things. She was never told that her tissue was perpetuated. Her family has never been paid any royalties.
There's a book on that, isn't there?
There is. She was black, and so this is another reason why the blacks are somewhat suspicious of white scientists.
This occurred in the 1930s, did it not?
I believe it did.
I-
I think her name was Helen Lang or Lane.
Henrietta
Lack.
Lacks.
Lack.
Henrietta.
Henrietta.
it.
Henrietta Lack.
Yeah,
Henrietta Lack,
I've read
yeah.
that book a long time ago.
Yes, yes.
And her,
So you can see there's a number of reasons that scientists have been very, without realizing it, sexist, and it has caused a great deal of animosity and distrust.
Sure.
And remember, there are such a small number of Black physicians. The Blacks have no, shall we say, knights in shining armor to protect them. That gets off the topic, but it's very relevant in today's world where we're concerned about equality.
Amazing. Thank you.
Mm-hmm.
Anybody else?
My understanding is that fetal tissue may have been used in testing some pharmaceutical products, but it is explicitly not used in the manufacture of the COVID vaccine.
It's not permitted by the FDA. So it's human fetal tissue, as like Bruce said, is not used to grow. It may be used in some testing, but it's not used to grow, to make the vaccine.
And if I may add something, this is Louis speaking, regarding those fetal cells. Those were harvested many decades ago, and the cells that are used today for some testing are the descendants of those cells. So there was 2 fetuses that were used many, many years ago, and none has been used recently, only the descendants of some of those cells.
That's right. The cells have been perpetuated in the laboratory, but they have no, they're not coming from humans today. That's exactly right, Louis.
Thank you. Good clarification.
For those who may want to know that the CDC in Atlanta has vials of smallpox, vials of wild polio that are kept in a very highly secure area, but they can be used for testing, but we're never going to let them out, we hope. But that's always a potential that they should get out. This is the problem with the COVID virus. Did it come from animals or did it come from a virology lab? That's what they're trying to find out.
I think they exhumed a body from Point Barrow, Alaska, from somebody that died of Spanish flu. And of course, from Point Barrow, Alaska, that's permafrost. Nothing decomposes. And they harvested the Spanish flu from this person to have it in lab, as like those other examples, just in case Spanish flu pays us another visit someday, so that they will be more prepared in coping with a resurgence of or recurrence of Spanish flu. Time will tell on that one. By the way, Spanish flu did not originate in Spain. It was just the first case was reported there. They've traced it back to a hog farm, and I think in Nebraska or Kansas.
Actually, the first cases were at an Army base in Kansas.
Right.
I think it was Fort Riley, Kansas, where they had the first big outbreaks among the troops.
Yep.
Or maybe in Nebraska. I don't know. Which one wants to claim it?
Actually, it was in Kansas.
Unfortunately, Spain got tagged with it.
Yes.
Yes, it was indeed in Kansas at the Army base, and the Army troops moving from base to base transmitted it that way, and eventually some of those soldiers ended up in Europe. The
That's
reason
right.
it was called Spanish flu is because the Allies and the Germans who were affected by the Spanish flu did not want their enemies to know how badly they were affected. So their press was suppressing any information about the effect on the troops. Meanwhile, Spain was a neutral country, and the Spanish press was reporting that there was a flu. Now, they didn't call it the Spanish flu because the news came from Spain. People in America in particular referred to it as the Spanish flu. The Spaniards referred to it as French flu because they claimed that it came from France. So that's the story on that.
Always
That's very
interesting.
interesting. Thank you.
I just got a question in the chat, you guys, that's asking if you can address the issue of ivermectin. Some of the non-vaxxers say it's the cheap way to prevent COVID.
I know a physician in the Dominican Republic that's been pushing ivermectin, saying it will cure COVID or prevent it. Now, this particular physician's already had COVID. The CDC says that that does not happen. There's no scientific evidence to justify that claim. It falls in the same category as hydroxychloroquine, which was pushed very strongly publicly as a cure or prevention of COVID, and it did neither. Finally, that one died down, and ivermectin is really not a big deal here, but you throw it in that same box.
Thank you.
Well, I think, John, we've thrown a lot of material at these folks. I hope they can absorb it, and I hope it helps them in their own lifetime decisions. It's been fun. I can say that Waldorf and Statler up in the balcony here, we've been throwing stuff at you. So hang on, you'll probably see us back someday again in the future.
You know who would fit in that balcony with us, just based on appearance? Bernie Sanders, third brother.
Yeah.
Looks just like him.
Yeah, it was
Bring
really
on
good.
Bernie.
It was really good. Even this psychology social work major understood most of your presentation. So I'm
All
very
right.
impressed.
That's what we wanted.
Yeah, I figured you did. That was awesome. Thanks.
Well, thank you, Richard and John.
Oh, you're so welcome. It was fun.
Yes, it was. And
Great. And we'll
I think
see you for CRISPR, right, Richard Swanson, on July 22,
yes, and CRISPR is not a drawer in your refrigerator,
right?
but we'll talk about it and have some fun with that one.
Okay.
Thank you, everybody.
Thanks, everybody. Have a great afternoon.
John,
Thanks.
my partner here is spectacular in helping me wade through. I make all kinds of mistakes and he corrects them.
Those mistakes are called typos.
Well, typos and not thinking through something, realizing that I haven't explained it. So
It's a two-way street, Richard. We've had a ball.
we enjoy it.
You know, when we're not working on these courses, we're just sitting around and talking science and just having fun.
Oh boy.
Good. Thought it was great.
You got to